All right, well, let me give my welcome to everyone, all the new students. Sorry we're not meeting face to face, but welcome to UC Santa Barbara and all the returning students and faculty. I'm glad to have the chance to tell a little about Henley Hall. So this has been a project of a lot of us here. Some of the folks, Steve Denbar is here. He was a big part of fundraising for this building, so I really want to acknowledge him. And obviously Jeff Henley in particular for making the biggest donation. So maybe I'll get started here. This is Henley Hall, so it's complete. We're beginning to move in. This is the north side. So the building is designed to be naturally lit, naturally ventilated. So the north side, all glass, as you can see. So it's nice on the inside. And this is the south side. And so on the south side, obviously you got to worry much more about solar heating. So that's what this umbra is around the outside to provide a lot more solar shading. And the windows are actually fairly sophisticated. They reflect light in the infrared very strongly, and but they're fairly transparent and visible. So you don't get very much solar gain out of it, but you can actually see through it. It's pretty nice. So again, the building is done. A bunch of us are moving in. They've done a really great job of landscaping it. These African tulip trees are just gorgeous. There'll be a lot more furniture out here soon. That's still being installed. But yeah, that's the south side of the building. So we started 2 years ago. It was finished actually on time and on budget in spite of a lot of things like COVID-19 and strike and things like this. It's about 49,000 square feet of space. It's designed to be LEED Platinum. So we're in the midst of applying for that designation. It hasn't happened yet. There's 18 labs, 17 faculty offices, 8 administrative and visitor offices, seating for about 174 students. There's a very nice lecture hall. 124 seat lecture hall you'll see, and 3 conference rooms. And again, this is a donor funded building. So it started by Jeff and Judy Henley. And then Sean and Brooke Byers came up with most of the rest of the balance. So very nice. And we started moving in September 1st. This is what the first floor looks like, just to give you an idea, and then I'll go into a little more detail on the airflow and energy efficiency. But there's a bunch of labs on one side. So this portion of the building is air conditioned and temperature controlled. This part of the building over here is not, so it's artificially lit and, well, not completely, but artificially ventilated. There's no air conditioning on that side. I'm proud to say there's actually two showers in this building. So for all of you who like to bike to work, there aren't very many showers on our end of campus, but there's one on the second and one on the third floor. A couple of nice conference rooms in the lecture hall you'll see in a bit. So this is the goal, as much natural lighting as possible. And in this portion of the building, natural ventilation as well. So actually the end of the building is completely open. So the first floor, there's glass for more security reasons, but the second and third floor, this is completely open, and same thing with over here. And so part of the intent was to have sort of an open atrium with offices around the outside. And we had that plan at one point. Facilities was very nervous about keeping this clean, and leaves and birds and all kinds of things. So in the end, there's a roof over the top of it, but much of this is completely open to the air. And in light of COVID, we're pretty happy that that's true. If anyone has any questions, by the way, I can't see the chat thing, so just speak up, just shout and I'll stop talking. Here's a little more detail on that. You'll see that the atrium is completely open. This is basically a big chimney. There's windows at the top that are electronically controlled. So again, Igor Mezik is going to run lots of interesting programs on optimizing the energy efficiency of this building. But the idea is to sense temperature inside and out and wind direction and flow and so forth, and pull basically air out of here on a hot day and then pull it in through the sides. And so that's the goal. The lecture hall is mechanically ventilated and cooled. Again, the thought being if you had 125 people there, that might get a little too hot. But like all of the spaces, there's sensors to detect if there's people in there. And if that is empty, then the lights shut off and the air conditioning shuts off. So it doesn't stay cool. And you can't sit there and set it to be running at 68. The system is smarter than you are. It'll take over. So I just want to run through a few slides on building it. So the first thing 2 years ago was to dig a big deep hole in the ground, and you may have seen these big piles of dirt all around the outside. And so we're all pretty excited. The building was started, and you had this big hole in the ground. And then the first thing they did was they filled it all back in again. And so again, what they were doing was compacting the soil. And so, you know, after a week of earth moving all around, we're back to a level space. And the next step then was putting in lots of piping and lots of steel throughout this, and then pouring concrete. So here's again, you can see all the steel work going in for the first floor, and then the steel work here for shear walls, basically, to keep the building from toppling over in an earthquake. We had a couple intense days of pours. You may remember there was warnings that went out typically on a Saturday. There was one day where they had 70 cement trucks come in pouring concrete. And that was the day where it had rained the night before. So they, you see the water here, they pumped it all out and were able to pour, but it wasn't so clear to me that was going to happen. But they had staged, you know, an awful lot to get that big pour in that day. A little more detail here. Again, a lot of steel in the wall, a lot of piping, as you can see here. I don't know if you can see my mouse very well or not. Hopefully you can. Again, here you can see the first floor is now done, shear walls, and now they're putting in the second floor. More shear walls, more piping. At this point now we have 3 floors on. We're starting to put the outside covering on the building. Putting the glass on the outside, on the north side in particular. The umbra on the south side to provide shading. And then this is that center atrium now. So here you can see the windows in the top that again are adjustable. And again, there's a roof over the top, and then again, you can start to see the steel work going in around the outside for this. This is the lab area. There's lots and lots of piping that went in throughout that. It was a huge amount for again, lots of wet labs and so forth. This is that atrium now getting finished. Again, starting to put up some of the interior surfaces. Again, more along the way there of that. Okay, at this point now it's fairly finished. So again, most of the floors are polished concrete and a lot of the surfaces are concrete. You can see here the windows on the top that all adjust, again, act like a giant chimney, get good airflow through this. This is one of the labs. This is actually Dan Blumenthal's lab. They're all typically 1,000 square feet in space and lots of overhead equipment, you know, gases and so forth delivered. So designed like ESB to be fairly generic, used for a wide variety of purposes. This is one of the electronics labs. So again, lots of shelving on the inside. This is more on the atrium again. And there's a lot of these patterns here that are provided on the outside as a bird strike. It's required. And obviously we don't want birds flying into all of this glass. And the inside it partially provides some small amount of privacy. Here's now done. You can see the polished concrete floors. This is Brett and Caitlin, myself, looking down towards the laboratory wing on the other end. So again, there's 17 labs. This is one of the wet labs. There's lots of chemical hoods here. And again, that's part of the challenge in a building like this, to make it energy efficient, but still have it work to be safe for heavy wet lab environment. But again, there's lots of sensors on all of the hoods. So if you open up a sash and you leave, then an alarm, not an alarm, but the building's going to note that there's no one in the lab, but the sashes weren't closed, and that's wasting energy, obviously. This is the lecture hall. So it's 125 seats. It wasn't quite done at the time of this picture, but why does this keep doing that? Sorry. Again, it's naturally lit. There are screens that come down that make it dark when we want to give seminars. At this point, the overhead projectors haven't been installed yet. Last step was to add landscaping, and so you saw that in the first picture, but that's basically, landscaping's done. They're still adding more furniture on the outside. And then over here, on the right-hand side, there's bike parking. And further to right, that's where presently military science is, but hopefully the materials building will be, engineering 3 will be built there next. And that's what it looks like at night. So let me stop and take questions. Go back and look at any pictures you want. Don't all talk at once.
Hey, this is Caroline. Thanks for the talk. I was wondering, are you getting an office in the new space?
Yes, I'll have an office. There's right now, it's primarily computer science people that have been assigned offices. So there's a big group that are moving out of Harold Frank Hall. Galen Movie and Dan Blumenthal are moving in there. And so yeah. Other questions?
John, one quick question. Why so much concrete?
Well, I mean, we live in earthquake territory. We have that much glass, you need shear walls. So, I mean, at least on the walls, that's what all the concrete is. In terms of the flooring, it's just something the architects like. I think UCSB likes. It's fairly, robust. Hopefully wears well. So again, like bioengineering, there's a lot of, polished concrete in bioengineering as well. So that seems to be the style. This is the chancellor shaking Jeff Henley's hand and thanking him for getting us all started. As you may remember, he donated $50 million to fund the building and also to endow the college. So at the time, it was the biggest gift that had been made on campus, and that's what he wanted to do, was sort of set a higher standard. And subsequently now, Charlie Munger has donated more, and that's great. So that was exactly what he intended. Picture on the right here, these are members of the Directors Council of the Institute for Energy Efficiency. So again, most of them have all been very generous donors to the Institute. So I showed this before. This is the first floor. So this is my lab. This is Steve Denbar's and Jim Speck and Suji Nakamura. This is Galen Moody's lab, in spite of the fact it says electronics. This is Dan Blumenthal's lab. These are offices, primarily visitor offices and Institute Energy Efficiency offices, conference room, lecture hall, so forth. This is the second floor, so it's primarily computational labs. Rich Wolski, Chandra Krintz, William Wang, Yifei, a bunch of those folks. Igor Mezik has the systems lab right here. So again, he's mechanical engineering doing research on building efficiency. There's a large group office here. So again, the style was much like computer science is everywhere. You'll see a picture of it. I thought I had a picture of it in here. So it's fairly open with cubicle seating. So as Jeff Henley kept pointing out, he doesn't have an office. He sits in a cubicle like everybody else, as does Larry Ellison. So that was his suggestion. And I think it's a good one. This is the third floor. So the 4 wet labs are up here. Again, another group office, lots of faculty offices. And here's some of the aspects that are energy efficient. So obviously, as I've emphasized, that there's a lot of building envelope aspects that were designed to minimize need for cooling or heating. The thermal insulation is significantly above the California Energy Code. The glazing on the glass is pretty high quality, low solar heat gain coefficients, but very good visible light transmission. Solar shade on the south side, and then operable windows to do ventilation. There is on the lecture hall, and I think in the labs, demand controlled ventilation. So the amount of airflow being pumped in there responds to demand rather than just running continuously. Similar system in the wet labs. There are chilled beams in all the labs, so there's not air conditioning. We're not, pumping chilled air around, but rather, cooled water that chills these beams. So the labs should stay very constant in temperature, and you don't have a lot of airflow, which is not good, at least for optics labs. And fairly sophisticated boiler design and so forth. And again, a lot of fairly sophisticated lighting controls that certainly should shut off when there's no one in the building. So I'll show a slide in a second that tells you where this building is. A typical UCSB engineering building has the energy use intensity. Love these units, right? These great engineering units. Kilobtu for feet squared. About 200. Here's a bunch of different, I just pulled this off the web. But things like, fast food restaurants might be 886. This building is designed to be 131. So hopefully it is very, very energy efficient. This slide shows how we got there. So hopefully a big reduction in HVAC, basically in particular. But everything's been looked at in a lot of detail to try and minimize it. We did have solar. It is ready. It's wired for solar voltaics on the roof. And we did have someone donate solar voltaics, so we were set there. But unfortunately, that company actually went out of business. So I haven't been gutsy enough to call them and say, you're still going to donate us photovoltaics. So that's sort of on hold at the moment. Any questions on the energy efficiency aspects? Okay, so obviously we're opening this in the midst of COVID-19. So just like all the other buildings on campus, we have a building committee, and that's Galen Moody, responsible for the first floor, Rich Wolski for the second floor, Phil Christopher for the third floor, and Brett Beisecker. And again, we have a plan. It's been approved by the Office of Research and EH&S. The offices aren't occupied yet, but will be hopefully in January. And again, the lab access is similar to what you're seeing with ESB or CNSI. So again, sorry, I don't know why my computer is fluctuating here. You have to do a daily wellness survey. You have to be in a lab schedule for the day. There's a maximum occupancy right now of 3 people per lab, and the building's open 8 a.m. to midnight, and you must wear a mask at all times. So that's pretty standard, what you'd expect from the other lab buildings on campus. And in terms of, flow, this entrance on the south side is the main entrance. You exit through the other 2. And primarily use the stairway to go up, and then you go down to the outside stairway on the outside. So let me give you a little overview of the Institute. So, we're all experiencing climate change very vividly in California. We're at extraordinarily high levels of CO2. And I showed that first slide of how do we get to emitting 20% of the CO2 where we are today. And it's very achievable, but there's a lot of good research that needs to be done to achieve that. And so that's the basic goal of the Institute is is how do we become more energy efficient, not how do we generate more electricity. So we don't do work on clean coal and carbon sequestration, but rather our focus is on energy efficiency. And this is the plot from NRDC, and this is our own study we had done before this is very close to this. But basically, how do you get to 20% of energy usage today, or if we don't do anything, where you would be in 2050? The biggest single element you can do is energy efficiency. The next biggest thing is cleaner grid. So that's people like Manoush and others, UCSB. Electrification is a huge amount. Decarbonization is huge. So we had a workshop today with lots of industrial and UCSB speakers, and they talked about all those aspects and how what we need to do to hit the intermediate goals at 2030 and certainly in 2050. And if we do all that, then the goal is to get to sort of 20% of the carbon emission that we're at today. So the Institute is 12 years old now, and it's about 40 faculty, 180 grad students, 12 research centers, about $40 million a year in research funding. We've been organized historically in these 6 pillars, and we've readjusted that over the last year, but Steve Denbar's led the lighting effort, and that's probably the most brilliant and successful example of energy efficiency out there. Going from incandescent light bulbs to efficiencies of hundreds of lumens per watt. I led the group in electronics photonics that includes, for instance, Umesh Mishra's work on gallium nitride electronics, again, very successful, very efficient switching. Rich Wolski led the group in computing, how do you make energy efficient data centers. We had a workshop on that 2 weeks ago. Igor Mezek leads the building and design area, and he was co-host of the workshop we had today on smart infrastructure. Guy Bazan led the effort in production and storage, and Sang-Won Su ran the economics and policy effort, which again, for this audience of photonics students, you may not see the advantage of it, the importance of it, but it's huge. And in the case of LEDs, the fact that California and US have banned the incandescent light bulb led to this rapid turnover and development of LED, gallium nitride LEDs, which were very expensive and prohibitively expensive before. So the problem is that LED standards are at risk, right? So the DOE right now is rolling back standards for everything. The automotive industry, appliance industry, lighting industry. They recently rescinded the LED requirement. And so we were moving forward and moving intelligently, but now actually that's been rescinded. And so, this area is hugely important. And with the present administration, we're taking a step backwards. But fortunately, California has its own standards, and for the automotive industry, for appliances, for lighting. And in fact, we had a CEC today that talked about that. So one concern is that, with Europe and much of the rest of the world phasing out incandescent light bulbs, then we could end up being basically the dumping ground for these ancient technology of incandescent light bulbs and compact fluorescence. So again, Steve Denbars is far better at talking about the energy savings that could be achieved. But again, we all know going from this light bulbs that are relatively inefficient to LEDs and now lasers, you can save a huge amount of energy. So that's what poster child for successful energy efficiency. We need to do it everywhere, in automobiles and in buildings and so forth. So this is what we call IE 2.0. This is the way we're organized now. So there's the one pillar is smart societal infrastructure. So that's the workshop we had today. Smart grid, smart buildings, solid state lighting, and then efficient energy storage. And this all came together. We had speakers from Southern California Edison today that talked about the challenges, when you have, during the middle of the day, huge amount of solar being generated now, and they actually have to pay to ship that energy out of the state because there's an excess of energy in the peak period. And so we need more storage, because that's obviously really a stupid thing to do when we have kind of the most expensive electricity in the United States to a large extent. So we can do much better than we're doing today. Second pillar here is energy efficient computing and communications. So again, that was the workshop we had 2 weeks ago. Data centers, optical interconnects, efficient processors. So again, electronics industry, very high capacity chips, switching chips, FPGA chips, we're all going to optical interconnects, right? Because you can't get 50 terabits of data on and off these chips, and that's where the industry is now. So 2 years, Broadcom's chips will all have optical I/O, and as well as everybody else. And so they were a speaker 2 weeks ago, and that's a big effort that we're doing there. And next week, we have a workshop on the food, energy, water nexus. And again, that's how do you make more efficient agriculture? So again, Chandra Krintz and Rich Wolski's effort there. In particular, lighting for more efficient agriculture that takes less water, a new, more efficient use of water and agriculture. And so that's in next week. So Friday, highly recommend you go see it. Then there's these 3 areas sort of underpin all of these. So obviously materials is hugely important for breakthroughs. AI is hugely important. And then again, this whole policy area. So these are the challenges in each of those areas. So again, we need to get to 50% renewable energy by 2030 and 100% by 2050. And the SCE speaker today indicated that's definitely what they're planning for within their grid infrastructure. I think we're all aware of how much energy it takes to train AI these days, and the statistics are just mind-boggling. We need to get to basically 1,000 times more efficient training for these situations. And again, in the case of the food, water, energy area, we were looking to double the production of food with less than half the energy and half the water that's needed. So that's really pretty exciting as well. So any questions on that, in that area of research? What's going on? Okay. If you haven't met these are the staff members. So Mark's been organizing these workshops this month. There's been one basically every week. Brett runs the staff, and if you have a contract that's run through the Institute, or if you're hired by the Institute, then you've got to know these 4 folks that manage all those contracts and orders and hiring and so forth. So it's a really good team, and they'll all be located in Henley Hall. Right now, they're all remote like the rest of us. So this is the Center for the Institute for Energy Efficiency. Part of that is the American Institute for Manufacturing, is located as part of the Institute for Energy Efficiency. Center for Material Responsible Machine Learning, William Wang runs. And then Solid State Lighting has a laboratory in Henley Hall. And if this Institute for Quantum Discovery that is funded, then they'll be located there as well. There's a bunch of industrial partners and research sponsors. Oops. Southern California Edison's been a partner for the last 10 years, and they have a very nice lab for testing out energy efficient devices. So if any of you are working on that, they can validate what we claim. Hewlett Packard's been had offices and labs in the Institute for the last, again, almost 10 years. And again, they work on high performance computing, again, using silicon photonics. ARM is one of the newest members of it, and obviously more efficient electronics is key. Ag Monitor used to be called PAWA, if you remember Olivier Jurfagnan, a graduate student from here. And he's been looking at how do you make more efficient use of water, basically. EcoMerit is Jim Dielson's company. Again, historically, his focus has been wind energy, but now the focus is tidal and wave energy. And then Facebook, Intel, Microsoft, Google have all been sponsoring research in the data center area. And Morton Photonics has been sponsoring research and been located originally within the Institute. Now he's moved out. So in terms of any questions on that? Okay, in terms of research going on there, I just wanted to highlight a few faculty members. So Igor Mezek, as I mentioned, has a lab that is looking at, again, gather all the data in the lab and in that building and devising algorithms to control it efficiently. But he has 4 million square feet of space worldwide being controlled by programs that have come out of his group. So that's really exciting. And there's a lot of buildings on campus that are managed by Igor's programs. So that's a key element of it. Eric Mazanet, he's a real leader. If you haven't gotten to know him, go see him. He's one of the IPCC lead authors, and looking at just this whole area of how do we reduce, this is his plot of, CO2 by 2050. And again, you can see, chemical processes, energy efficiency, fuel, are all big areas of improvement. Manoush works on smart grids. And again, I think we're all aware of basically how fragile our grid is today, and what a big problem it is, right? As we go towards having a large amount of renewable energy and solar, which is good, but during the middle of the day we have excess production of energy. You have to dissipate that somehow, and when there's major outages, the grid is not all that resilient to changes. If we all have electric cars, which I think by 2050 most of us will, certainly all the new purchases will be, then we've got the issue of 240 volt, 60 amp charging going on. And so again, part of Manoush's research is on how do you motivate people economically and how do you model it and basically efficiently not take the grid down when we all need to charge our car when we get to work during the day. So that's really interesting bit of research. One of the labs will be the one that Suji and Steve Denbars and Jim Speck have. And again, as I think you're all well aware, huge advances in gallium nitride LEDs, most recently, of course, in gallium nitride lasers and combining those with phosphors. And again, a very successful effort, and really glad to have them in there. And then most recently, as shown on the lower right here, using UV LEDs for sterilization. So Steve, you're in charge of keeping our buildings safe for us all. Phil Christopher is focused in the chemical engineering area. They use a lot of energy for all of those chemical processes, and his focus is on catalysis to be more efficient at these processes. And we're all aware of the importance of catalysis to make that successful. There's a bunch of computer engineering, computer science professors in the building. And one example is Tim Sherwood. And again, his range of research is, I think, a lot wider than probably most of you are aware. I mean, I've been aware of what he does for data center research, and he's really led a lot of that. But he's also doing supercomputer, superconductor supercomputing. And so I was not aware that was a focus he's working on as well. Chandra Kritz and Rich Volsky work on smart farms. And again, we can be much more efficient with our use of farming. We have more sensors. And again, in these remote areas, you don't have a lot of connectivity, you don't have a lot of power. So how can you have Internet of Things sensors that can collect all the data and make much more efficient use of farming? William Wang is a world leader in artificial intelligence, machine learning, and he's been working on how do you do this much more efficiently, because as you've seen the statistics, to train these modern machine learning algorithms takes huge amounts of energy, and that's his focus. There's 3 laboratories that are focused on quantum computing, quantum photonics. Galen Moody runs one of them, and this shows using these high Q gallium arsenide resonators to entangle photons, right? So gallium arsenide is very nonlinear, and so you get very high levels of photon entanglement, and that's his focus. Dan Blumenthal works on, again, data center, high efficiency data center, partially by making very narrow line lasers that Again, you can do coherent transmission, but you don't need to have power-hungry DSPs control the frequency or wavelength of that, as well as applying it to optical computing and atomic time clocks. And so again, going now into the visible and building these MOTs, right, to store atoms. I will have a laboratory there. So, folks in my group has been silicon photonics, widely tunable narrow line with lasers. So again, maybe tunable over 110 nanometers, but yet with, 120 hertz Lorentzian line widths. And we've locked those to resonators and gotten the line widths down to just 3 hertz. Some recent work by Warren and Jin looks really, really exciting there. We work a lot on optical synthesizers. And again, you need to generate an octave of bandwidth and lock that so as to know the frequency you have within a hertz. And this shows stepping the frequency of a laser in sub-hertz steps. And so the accuracy is sub-hertz as well as the precision. So overall, get in 1 part in 10 to the 15th. And then using quantum dots in particular for quantum communications and also more efficient devices, and building optical phased arrays again, for things like optical LiDARs and hopefully much more energy efficient. So one of the labs in the new building is a data center lab. And so again, lots of faculty are involved in that. And so, some of it is more efficient cooling, either water cooling, air cooling. Some of it is more efficient computer architectures. Some of it's more efficient processors. Some is more efficient photonics. Any questions on that? I'm about to end here. I'll just mention a few things that at least you've probably heard of. So we do offer seed grants, and we awarded 4 last year in areas like smart grids, neuromorphic circuitry, again for artificial intelligence, working on protecting the California citrus crop from the pests that have come in there, and then green AI. This year we just awarded, sorry about that, 3 grants. Quantum regenerative learning from Zhang and Moody, control mechanism for energy management by, again, Manoush, and then passive water harvesting by solar energy. So again, generating hydrogen. So these are awarded every year. Deadline is August 1st. We have another fellowships, again, roughly the same deadline, July 31st. We've just announced the newest fellowships. And as I mentioned, we run lots of workshops and seminars, typically Thursdays at 4 o'clock. And these are the 3 workshops we've been running on Fridays. And so we had the Smart Societal Infrastructure today. Next week will be the Food, Energy, Water Nexus. So again, you're all invited to attend those. Send email to me or Mark Abel if you don't see an invite. So with that, I'll end, and be glad to take questions.